Okay, so today I have 5 problems this week that we don't talk about. First three, based on what people have done so far, seems to be relatively straightforward, and then the last two are probably a little bit harder. So let's get to it. Okay, so first problem, scheduling. So I assume that people have read the problems. I'm not going to really go over it too much, but the idea is that you're given, first of all, the number of student course requests up to 10,000, 100,000, I mean. And then each of these requests has 3 parts: the student's first and last name and the course that the students want to take. You can assume that each name is a string of at most 1 to 20 characters or uppercase characters, and course is 1 to 10 uppercase letters and digits. If a student requests a given course more than once, only the first such request will be considered. And then, so at the end, you want to print out for each course how many people are requesting it, and you want to print them in sorted lexicographical order in terms of the course. All right, so basically what you have to do, of course, is you have to have a way of remembering for each course who are the students. You can't just keep track of how many, because you need to know if they're duplicates. Some student requested something multiple times and you only count such things once. So here you want to make sure that the students, I need to keep track of the unique ones and how many there are, but I must remember the names, otherwise I wouldn't be able to tell if I have duplicates. So here, because I want no duplicates, I'm going to have a set. A set of what? It's going to be a set of 2 things, first and last name. And so I'm going to have a set of pair string string. Okay, so we'll just use a pair to store the first and the last name, have a set. So automatically, if I insert multiple copies of the same first and last name, it will just get rid of the duplicate. So this is how I'm going to deal with the duplicates. And then here, so this is how I deal with, how many, the set of students that are enrolled in each course. But now I have to map a course to the list of students or a set of students. So that would be a map. So at the end of the day, what I'm going to do is I'm going to use a map that takes the course, which is a string, and map it into a set of pairs of strings. Okay, so this is kind of maybe a little bit complicated in terms of the structure of this, the data structure. It's sort of nested, 2 STL containers nested within each other. But if you use this, then it's very simple, because every time somebody gives you a first name, last name, and a course name, all you have to do is look up the entry of the map corresponding to the course and insert this pair. At the end, all you have to do is loop through the map, because this is a key. This is a course name by default in maps. It's automatically, when you loop through it, it's automatically looped through in alphabetical or lexicographical order. So you don't have to worry about sorting anymore. And then for each entry, simply print out the course name along with the size of the set. Okay? Now you can maybe do it yourself, write your own data structure, but there's really no point in doing that. If STL with containers would be good enough, because it's much easier to use. So let me just very quickly show my solution. I don't know if other people do similar things, but this is how I would do it with STL. Okay, so you read in the number of course requests, and then here, this is my, what I call frequency, how many, I guess you can also call it enrollment, whatever you want to call it. This is my map that maps a course to the class set. It's pair string string. Okay, I set up pair string string, and then just go through for each course request read in the first name, last name, and the course name. And I simply use frequency square bracket course that would look up the map entry for that course, that which will be set. And then I have to insert a pair consisting of first and last name. And I've said before, but if you don't remember, in C++ STL, the word emplace means that you put into the container an object that is constructed by these two arguments, by whatever argument. So a pair requires two things to construct, and the two things to construct is first and last name. So they will construct the pair and put it in the container. Okay, if you don't want to don't want to use emplace, you can first create a pair using make pair, for example, and then insert into a set. Okay, but emplace is sort of a shorthand. And then finally, once you have built this map, all you have to do is loop through the list, loop through this map. And this is a range-based for loop that's easily written to take apart each entry. So each entry is a pair of the course name and the set. So I just wrote auto square bracket name comma s, and that would take each entry of the map and assign the key to the name, and then the set to s. And then I just print the course name followed by space followed by the size of the set. Okay. So this is it's the relatively simple problem. How fast you manage to do it and how accurately you manage to do it depends on how careful you are. But if you know STL quite well, you can use these functions and containers to your advantage so that you don't have to do a lot of work writing this code. Okay, so here it is. Again, if you want to consult further, you can look at my GitHub repository for all the solutions that I have. Okay, next problem, darts. So you have a game of darts. There are 10 circles of radii 20, 40, up to 200. Center of origin, and depending on which circle, the smallest circle enclosing or passing through the hit point has this radius of 20 times 11 minus p, then you get p points. And no points are awarded for a throw that misses the largest circle. The task is to compute the total score of n throws. So you have t cases, and then each case starts with a number of throws, which is up to 1,000,000. And then each of the next n lines contains x and y, which are up to 2 plus or minus 200. And then it says the sum of all n, the sum of n across all t cases at most 2 to the 21. What does that actually mean? Well, you're going to have to process each throw. You have 10,000 cases at most. Each one has 1,000,000 throws at most. So if they didn't tell you this last one, then you can potentially up to 10,000 times 10 million throws to process. And that's a lot. That's 10 billion. And basically, you probably, whatever time limit that they give you, 4 seconds, you probably won't be able to, well, I shouldn't say probably, you will not be able to run in time in 4 seconds if the only thing you do is to read 10 billion things, even if you don't do any calculations. So what they're saying is, even though each case can have up to 1,000,000 and there are 10,000 cases, the total number of throws that you have to process is at most 2 to the 21, which is about 2 million. Okay, a little bit over 2 million. So basically, they're saying that there might be some big cases, but there cannot be too many big cases. Okay, anyway, and then for each case, you're supposed to print out the sum of all the scores across the n throws. So really, all you have to do is take each throw, right, and then figure out which circle it lands in, if any, and then add up the scores. All right, so, oops, why did it? Okay, here we are. So you have circles of different radii. Okay, assume that I can draw a concentric circle better. And then you have, darts like this. And you have to figure out which circle it lands in. Remember that if you land in a small circle, it also lands in any of the bigger circles, right? So this one lands in this second largest circle, but it also lands in the largest circle. You want to find the smallest one that works. So what you want to do is just, start from a smaller circle and just do a linear search and see which one encloses the dart throw. You do have to remember if you read it carefully, that landing on the boundary, so if I land right here, landing on the boundary counts as landing inside. Okay, so this is one thing that you have to remember. If not, then just make sure you read that. Just read the statement carefully. If the smallest circle enclosing or passing through the hit point. Okay, so if you just land on the boundary, it still counts. So that's one important thing. So then the question is, how do you figure out whether you land or not, right? So given a particular circle, whatever that circle is, you have a certain radii, or radius, and then you have a dart throw. Maybe it's here, maybe it's there, maybe it's right here. And the way that you figure out whether you land or not is to compute the distance, right? Compute the distance from the center, from the origin to the dart throw, and ask, is it less than or equal to the radius? Okay, so less than means you're within, equals means you're right on the boundary, and greater, of course, means you're outside. Okay, so how do you compute the distance, right? It's Pythagoras theorem, x squared plus y squared square root is less than or equal to r. And you might just start to code this. However, one of the things that you should realize is that x, y, and r are all integers. So r is an integer, no problem. X squared plus y squared are also integers, no problem. But when you take the square root, it could be floating points. And whenever you have comparisons of floating point, you always have to worry about, what if I do 3 squared plus 4 squared square root? We know that this should be 25. 9 plus 16 is 25, so it should be 5. But because these are floating point numbers, there is a possibility that you end up with something like this, or maybe 4.9999. And then if you try to compare whether you are 5 or not, this will give you the wrong answer, right? This one will give you the okay because you're still within. But if the rounding rounds you a little bit up, then things could be problematic. Okay, for small numbers like this, it probably wouldn't happen. But you want to be, there's no reason to take this risk, because all you have to do, instead of computing this distance, it's less than or equal to the radius, you can compare instead the square of the radius against the square of the distance, right? Because if d is less than or equal to r, this is true if and only if d squared is less than or equal to r squared, provided that d and r are both non-negative. Okay, if d and r can be negative, then this doesn't work, because when you multiply by an inequality by negative numbers or square them, it can reverse the inequality. But because we know that distance and radii are always non-negative, we can say that comparing the distance and the radius is the same as comparing the distance squared and radius squared. And when you compare the distance squared, why is that better? because distance square means that you don't have to take the square root. You get rid of square root. And now x squared plus y squared and r squared are all integers. There will be no possibility of any rounding errors. Also, because x, y, and r are all fairly small, up to 200, at absolute value up to 200, so square of them, square, it's at most 40,000. Two of these together is at most 80,000. The most important thing is it going to overflow in 32-bit integers? And the answer is no, you're well within bounds. Okay, so you don't have to worry about using bigger integers. And that's it. So this is a main crux of this problem. Of course, you still have to do some bookkeeping to figure out which is the smallest circle that holds the throw, and then keeping track of the actual score. So I'm going to just show you my solution here. Okay, so first the main, I read in the number of cases, and then I just loop through and call solve, which solves each case. So I always do this so I can write a function that only deals with one case, and then I don't have to worry about the indentation level and so on. And then in my solve that solved each case, I first read in the number of throws, initialize the score to be 0, so I keep track of score. Again, there are at most 1 million throws. Each one has at most 10 points. So this is also within bounds of a 32-bit integer. This is at most 10 million. Then I just loop through each throw, read in x and y, and compute a square distance, x star x plus y star y. Now, don't use something like pow x comma 2 because it's a floating point operation. It is not an integer operation, so you should avoid that. When you write x times x for squaring, that's actually better because that keeps everything as integer calculation. And then here, I'm not quite sure why the indentation looks weird here. But anyway, the point is now I'm looping through the circle with the biggest points, 10. It's the smallest one. So my linear search goes from the p equals to 10 down to 1. And then I ask if the square distance is less than or equal to, and they tell you that when the point is p, the radius is 20 times 11 minus p. But I need to square it, so I need to multiply twice. So I have 20 times 20, 11 minus p times 11 minus p. So this is the square of the radius. If you don't like that, you can assign r to be 20 times 11 minus p, and then you put r times r. In any case, if the distance squared is less than equal to the radius square, I will increment the score because now I found a circle, the smallest one, and because this is going to be the smallest one that works, all the other ones later on will also work. So I break, right? So if I found a small circle, I don't want to include any of the other circles that also work. Now, if none of them works because you throw it so far out, then this loop will just go through all 10 circles without adding any score. So this will still work. It's always good to confirm that, at least in your head, that this is what you want. In the case when the search doesn't work. And then after you process all n throws, all you have to do is print the score. Now for this problem, maybe you can get away with not doing distance square comparisons. I'm not absolutely sure. Actually, can I edit and resubmit? Let's try that. If I actually use square root, the most difficult thing to check if you don't use integer calculations only, it's when it's exactly equal. So if somebody throws something right on the boundary, but because the numbers are relatively small, up to 200, you probably are okay with the digits of precision. But let's see. Yeah, unfortunately, it also still works with these numbers. But if the numbers could be bigger, then with more digits, then you might not be able to get away with using square roots. Okay, so get into a habit of not using square roots if you can avoid it, especially for things like distance comparisons. Get into the habit of doing comparison of squares, so you don't have to worry about round off errors. Okay, next one, volume. So you have a bunch of people in circles sitting 1, 2, 3 up to 8, and then you have this box that's passed around. Every time somebody asks a question, you either get it right, get it wrong, or skipped. And then if you get it right, you pass the box to the next person. If you get it wrong or you skip, you hold onto the box and you keep going, and it will explode 3 minutes 30 seconds. So you have to figure out which one is going to hold on, have the box when the box explodes. Okay. So basically what you have to do, you have to keep track of who has the box right now, and you have to keep track of what is the current time. Right? So 20 means from the time you get the box to the time you give an answer, it takes 20 seconds. There's not really too much to say, I guess. I don't know if I need to draw anything out, but you have a circle. Okay, so you have a circle of people, always 8 of them. And whoever has the box first, when they pass it, they always pass it to the one on the left. So it goes this way. So basically, if you pass it, you have to find a way to go from 1 to 2 to 3, all the way up to 8, and then back to 1. Right? So basically, you add 1, and when it's more than 8, you go back to 1. I usually like to convert things back to 0 base, like this. Why? Because wherever you are, the next one is always k plus 1 mod 8. You cannot do this with 1 to 8 because 8 mod 8 would give you 0. Okay, so if you want to use this trick without writing any if statements, then you need to convert to zeros. For this problem, it really doesn't matter if you convert to 0 base or keep it 1 base. You can do it either way. The other thing you have to do is just keep track of the current time. And when you get the box, right, and by the time you answer a question, if you take the box before 3 minutes 30 seconds, and by the time you answer the question is 3 minutes 30 seconds, then the box explodes in your head. And that's really all you have to do, which is to keep track of the time and keep track of the position of the box. So here's my code. It's fairly simple. You first read the index of the person starting with the box, and I subtract 1 because I want to convert to 0 base. I read in the number of questions. Current time is 0. That's when I start. For each response, I read in the time it takes to answer and the response. Update the time, increment the time by that much. And if the current time is now greater than or equal to 210, that's 3 minutes 30 seconds. In seconds is 210 seconds. Then it means you explode. So you print out the name, the index of the person holding the box. But remember, because we subtracted 1 to make things 0 base, I have to print k plus 1 to print it back in 1 base and then break. So it exploded, I'm done. Otherwise, either the answer is T, N, or P, and the only time that I have to update where the box is it's if I answer the questions correctly, so that's T. And so if the response is true, then I just update the position with this relatively simple arithmetic operation. Okay, so when things goes in circle, I usually prefer to use modular arithmetic because it makes things easier without any if statements and so on. But in order for that to work, you better make sure it's 0 base. Okay. Okay, so those are the 3 easier problems. Now we get to something that's a little bit more involved. All right, Geppetto, I don't know how you pronounce it. Anyway, you're making a bunch of pizzas. There are n ingredients, 1 to n, and then there are m pairs of ingredients that cannot be on the same pizza. Okay, two pizzas are considered different if there's an ingredient index I that's on one pizza but not the other. You want to know how many different pizzas you can make. Okay. First line, there are two integers n and m, and it's up to 20. Okay, so there are up to 20 ingredients. There are at most 400 pairs of forbidden pairs of ingredients. All pairs of ingredients are not necessarily distinct. Some pair could occur multiple times, so we have to worry about that. What else? Are you allowed to have a pizza with no ingredients? Like, can you have pizza with 0 ingredients? Doesn't say, but you can try. Does it say that? You make pizza, blah, 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 every simple, but first, sometimes these cannot mix and create additional complications. Okay, it doesn't say that you cannot have a pizza with no ingredients, but we can confirm this. Okay, there's 3 ingredients. 1 and 2 cannot go together, 2 and 3 cannot go together. And so actually it's easier to look at this one. 3 ingredients and 0. So all possible combinations of 3 things are included. And that includes the empty set as well. So when you start talking about, combination, empty sets, and so on, I hope you see where I'm going with this. Each pizza is described by a subset of toppings ingredients that you're allowed to use. And so we're looking at a subset of 20, at most 20 things. And so now you have to remember, or you have to know that if you have n things, the set of possible subsets, there are 2 to the n. That's the power set, right? So there are at most 2 to the 20 different subsets. 2 to the 20 is a million, which is not that much. And they give you 1 second. So what we're going to do actually is just try all possible 2 to the 20 subsets. And for each one, check the 4 up to 400 pairs. Is it, does it violate anything? And if not, then you count it. Otherwise, you don't count it. And that's it. So really, the main question is how do you do all subsets? And here's my code. It looks a little bit scary, but let's go through it one line at a time. All right, so first thing, read in n and m. Then I have a pair, an array of pairs, which are the bad ingredients. So I read in the bad pairs. And now what I'm going to do, answer is how many different ones I have, how many different subsets are good. And this is a standard loop that I use to go through all possible subsets of n things. Okay, I'm going to take an integer s as an n-bit number. Okay. And this n-bit number, it's going to start from zeros. So let's just say 6-bit. And as it counts through all the, actually, why don't I make it just 3 bits so I don't have to write so much. Yeah, why can't I change the eraser size? Not sure why I'm stuck with this small eraser. Okay. So where this counts through is 1. This is a binary patterns of the numbers 1 0 0, 1 0 1, 1 1 0, 1 1 1. And remember, this is 0 1 2 3 4 5, 6, 7. And this one shifted, this is 1 shifted to the left, binary bit shift n positions. So when n is 3, 1 shifted to the left 3 steps would be 0, 0, 0, 1. And that's 8. So 8 is too big for 3 bits. And so this will count from 0 to 7 and steps through all possible subsets of size 3 if you use the bit position. This is bit position 0, 1, and 2. If, for example, bit 1, if it's a 0, it means that the item number 1 or ingredient number 1 is not selected. And when it's 1, it means ingredient number 1 is selected. Okay, so this is a little trick that you can use to easily go through all the subsets. So for each integer s, it will give you a subset. Let's say this one. And now what you're going to do is you're going to have to figure out if it violates anything. So what I'm going to do is I'm going to first assume that it does not violate anything. So the good is true. And then I'm going to go through all the pairs M that are bad. And as long as it's still good, I keep looking for another pair. So as soon as I find a pair that's, as soon as I would discover that this subset is not good, I stop searching for pairs because finding one pair of bad ingredients is good enough. I don't need to find all pairs. So how do I figure out if it's still good? Well, I look at the pair. Okay, so the pair might be ingredients 1 and 2. So what I do is I take 1. Oh, by the way, this is 0 base. Sorry, this is 1 base. So 1 and 2, I actually want to change it to 0 and 1. Okay, so this is 1 base ingredient that they give you in the input. So I actually want to change it to 0 base. So that's why you see the -1 and a -1 here. Okay, so now I want to know if the sets that I have both 0 and 1 bit turned on. How do I do that? Well, what I'm going to do is I'm going to take this 0 and I take 1 left shift 0 times, and that will give me this. And take this 1 and take 1 left shift 1 times, and that will take me this. And I would say, take this set here. I do bitwise AND. Right? So if this is a set 0, 0, 1, 1. So this is my set. And then my mask of 1 mask. And then I do a bitwise AND. It will be non-zero. If there's any bit in common, it'll be non-zero. And because the mask only has a single bit that's turned on, it also basically says, is this bit on or not? So basically, I'm asking, does the mask... So the first part says, the mask has the first bit on, the first ingredient bit on. And then this one says, does the subset have the second ingredient? And if both of them are present, then it's bad. So if it's not the case that it's both of them, then good can remain true. Okay, so you can do many, many things here instead of writing it in such this much more convoluted way than I write it. You can write if the first bit is on and the second bit is on, then good equals false. The way that I wrote it here, which is maybe more confusing but also more concise, make use of Boolean operations and bit operations to avoid writing any if statements. Okay, anyhow, once you have done this, once you have checked all of these pairs, if at the end good is still true, that means you have not found a pair of ingredients that are bad. So now I can increment the count by 1. And that's it. And then at the end, it process all the subsets, and then you can answer, right? Now, this is maybe you say, well, do you really need to go through 2 to the n subsets? What if you incrementally, so you can actually do this recursively by trying all subsets, by saying let's say pick the first ingredient or don't pick the first ingredient. For each branch, you recurse. Then you pick the second ingredient or don't pick the second ingredient, you recurse. But as soon as, let's say, you pick the second ingredient and you also pick the first one, and that's bad, you don't have to recurse that branch, and you can prune off a lot of the unnecessary searches because you know that there's no point continuing with anything that has the first 2 ingredients chosen. And you can do that, and it will be much faster. However, this problem is relatively small, so I chose to do it this way because it's much easier to write and much faster to write. So this is another technique or trick that you should have under your belt, which is the idea of going through all possible subsets using what we call bit masks, okay, by taking integers as n-bit numbers and then using the binary pattern to indicate which elements is in the subset and which ones are not. Okay, the last problem that I want to talk about is a type of problem that almost everybody hates, geometry. These are, geometry, it's always, problematic sometimes because people forget how to do geometry, or maybe they were never comfortable with it. But these are high school level. There's nothing, well, actually, there's one thing that you might not know. Okay, so you have these triangles that they give you. They give you by lengths A, B, and C. And you hang, oops. So you hang a triangle like this, and you only hang it at a corner. And then the triangle can rotate, can tilt whichever way until it somehow settles into some kind of equilibrium. And then you have to figure out for each triangle how long this is, because you're going to add all of them up and figure out how long the rod is. Okay, so you have to figure out, if they give you this lengths A, B, and C, that somehow you have to know that the triangle settle in this orientation, and then this is the width that you have to keep track, you have to compute. So there's a little bit of math and a bit of, I don't know if you call it physics. So we have to figure out how to actually deal with this problem. Where did my, okay. All right, so let's start. You have a triangle. Maybe it's like this. This is A, this is B, this is C. And you hang it, and then somehow it rotates to, let's say, this orientation. How do you know that it rotates to this orientation? Well, the idea is that if you, whichever orientation it rotates to, and you draw this line down vertically, then the area here and the area here should be exactly the same. If you cut a triangle into 2 equal halves, by equal I mean area, then it would be balanced. Okay, so that's maybe this is a little bit of physics, I guess, the center of gravity and all that stuff, that when it actually settles and you draw a line straight down from the string that you're hanging the triangle, it will cut the triangle into 2 equal parts in terms of area. So that's, I don't know if I call it fact number 1 that you have to figure out. The second part is, if I give you a triangle, whatever triangle it might be, and let's not even say that I have already rotated to the right orientation, like this. Where does this line go so that the area of these two are the same. Okay, so that's the second question is, where should I go to this on the other side to divide the triangle into two equal halves? All right, so let's, I don't know when you learned this. So let's go back to triangle. We'll draw it like this. You're trying to draw a line from here to here somewhere. And you have A1 and A2. What is A1 and what is A2? Right? How do you compute the area of a triangle? Well, in order for you to compute the area of a triangle, we know that the area is base times height over 2. Now, where's the height? The height, it's here. And it doesn't actually matter where you slide this thing, this point, the height is always the same. But the base 1 and base 2, of course, as you slide this point, base 1 will increase and decrease, and base 2 would also do the opposite, right? If you increase base 1, base 2 decreases. The important thing is to say is that base area 1 is base 1 times height over 2, and area 2 is base 2 times height over 2. So if you want to make A1 and A2 equals, what does it mean? It means that base 1 and base 2 have to be the same. In other words, all you want to do is take this length and cut it in half. So cut it in half. How do I draw this? I guess you draw marks like this. So these two parts are the same. In other words, given the original problem, so the original problem is like this. You have A, B, and C. You want this to be C over 2 and this to be C over 2. Okay, and we'll call this D. And once you have managed to cut this into two halves, and you have a D, then you have to figure out, so let's say you rotated this, and D is like this. Then you have to figure out how far it goes this way and how far it goes this way. Okay, so there are a number of different ways you can do this. Basically, you have to use trigonometry. There are lots of different ways you can do this trigonometry. But let me show you what I would do. I have three sides, A, B, and C. So the first thing that you might want to figure out is what is the angle here? Okay, why do I want to do this? Because if I know the angle here, then I can use, let's say, this, let me use a different color. I can use this triangle to figure out the length of D. Okay? And whenever you have a triangle, hang on, let me use a little bit different letters, lowercase, A, B, and C, and there's a theta here. There's something called a cosine law, which you hopefully remember from high school. It says that C squared is equal to A squared plus B squared minus 2AB cos theta. We know the three sides. We want to figure out the angle. So here, I'm looking at a big triangle now. I'm looking at this angle. So I have to be careful what is my capital A, B, and C. It says, This C is the side opposite to the angle, which now it's the capital B. B squared is equals to A squared plus C squared minus 2AC cos theta. Okay, so that's cosine law. And I can solve, because I know capital A, B, and C, I can solve for cosine theta equals to A squared plus C squared minus B squared divided by 2AC. And then theta would be A cos, the inverse cosine of this thing. Okay, so I can figure out what cos theta, I can figure out what theta is. Actually, I suppose I don't even care about what theta is. I just need to know what cos theta is. Because now I'm going to do the same trick here with the smaller triangle. And I'll write d squared, it's equals to a squared plus c over 2 squared. So I look at the smaller triangle. Minus 2a times c over 2 times cos theta. So if I already know cos theta is this, I can plug that in here. And now I know what d squared is. I know what d is. Okay, so now that I know what d is, how do I know this side and this side? Okay. Remember that the areas are the same. A1 and A2, they're really the same area. Well, this is perpendicular. So the area, D is basically the base of this triangle. So the area, A1, it's actually D times height over 2. We need to know what the height is. So the height is 2 times area 1 divided by D. And this is the same because area and 2 are the same. So you compute h and then multiply by 2 and you're done for that triangle. But you need to know the area of this. So how do we know the area? Right? There are a bunch of different things you can do, I guess. But the easiest thing is to use something called a Heron's formula. And this is in my code library. Heron's formula says that if you know the lengths of the 3 sides of a triangle, then applying the formula will give you the area of the triangle. And you know that A1 and A2 are simply half of the area of the original triangle. So once you know the original triangle's area, divide that by 2 would be the total area. And then you can apply this formula to give you h. If you read my code, you'll see that I do something slightly different because maybe I wasn't really thinking as hard. So there's some code that might be a little bit redundant, but it does compute the right thing. Namely, I didn't bother using the fact that these 2 sides are the same, so I actually computed twice. So I'm not going to show you the code. You can look it up. So Heron's formula, and you can look up Heron's formula. It's credited to Heron of Alexandria for finding the area of triangle in terms of the length of the sides. If A, B, and C are the lengths of the sides, then the area is this square root of S times S minus A times S minus B times S minus C, where S is the half of the perimeter. Okay, so if you just use this formula, you can get the area of the triangle if you just know the 3 sides without figuring out the base and the height and all that stuff. Right, so this can come in handy sometimes, and I want to show you this. And I guess, yeah, this is a little bit scrambled now, but if you go through how I derive everything, then basically what you have to do is you first, oops, you first figure out this cosine theta from A, B, and C, right? From the given A, B, and C. Then you figure out D from here. And then with Heron's formula, and then divide the total area by 2, you figure out A1, which would then give you H. Multiply that by 2, and that will give you how much each triangle takes up in terms of the length of the rod. And then you repeat that for every triangle, add them all up, and that's your answer. Okay, so this is, I guess, this week's set. I'll post a video so you can look at it, and then Wednesday I will post another set of problems. See you later.